All right. Good afternoon, everybody. Good afternoon, Reese. Happy Friday. How we doing? Amazing. Yeah, it's a beautiful day out there, isn't it? Yeah. Spring is here. Feels like spring. And yesterday was the first day, right? Wasn't yesterday? Yeah. Yesterday was the spring equinox. Yeah. So it's acting like spring, which is nice. Okay, well, I think we're going to jump right into it because we kind of have a lot to cover by finishing this up and then getting into the immune system. So I did want to just kind of make sure we're all you guys got the answers at least for a couple of these questions on the TBL activities here. Again, as I said before, make sure that you know everything on this slide well. Um, I always like the clinical applications to every part, and this is one here for sure for the blood clotting stuff. So different blood clotting drugs and how they work. And so this question here is related to blood clotting as well. So the a blood clot itself that's stable, that's stuck in one individual place is called a thrombus. Okay, so that's this one, thrombus. Okay, a blood clot that gets dislodged and just going through the bloodstream. This is called an embolism. Okay. Oh, sorry, an embolus. Yeah. And then when it actually gets stuck somewhere, the one that was floating through and it gets stuck somewhere, then it's called an embolism for the last one there. Okay. So if you've heard of like a pulmonary embolism, right? It's like when there was a blood clot in somebody's leg or something and it came free and then got stuck in their lungs, right? So that's the idea there. Okay. Kind of another key clinical application here is that part of the blood clotting process, that last stage of the blood clotting process, is breaking up the clot. So it's called fibrinolysis, right? So breaking down a fibrin. That is done by turning plasminogen, which is a plasma protein that's always in our blood, turn that into plasmin. Plasmin is the thing that breaks up the clot. Okay. And the way that we activate plasminogen is by this enzyme here called tissue plasminogen activator, TPA. Okay. And so if you've maybe you've heard of this drug, but we can make it synthetically. And pretty much if you put TPA into somebody's body, it turns all the plasminogen into plasmin and it breaks up clots everywhere, right? And so this is a very common treatment for someone who's having a heart attack or a stroke. And if you get them to the hospital early enough, within like a 2-hour window of onset of symptoms, and there's different protocols for that. It's not always 2 hours, but something like that. Then you can administer TPA, and it can save some brain tissue during a stroke. It could save some heart tissue with a heart attack because it breaks up that clot and allows the blood flow to continue. The problem is with a stroke, a stroke can be one of two types. It can be a type that's caused by a blood clot, and then that blocks blood flow beyond that. That's called an ischemic stroke. Ischemia means lack of blood flow. Or it can be a hemorrhagic stroke where a blood vessel in your brain breaks open. Okay. If it's a hemorrhagic stroke and you give somebody TPA, that's not a good thing, right? Because we're trying to get that bleeding to stop in the brain. You give them TPA and you're just creating more bleeding, right? So with stroke treatment, they're always going to do a CT or an MRI first to see if see which type of stroke it is, whether it's a hemorrhagic or ischemic stroke. And so, yeah, it says which answer here is not true. So it would be this one. TPA will only work for hemorrhagic strokes. It's the opposite of that. All the other ones are true, that the treatment is very different for the two. It only works for ischemic strokes. If you give it to somebody with a hemorrhagic stroke, it can be fatal. And giving it to someone with an ischemic stroke could save some of their brain. Okay. Questions on that one? Yeah. Colby? It could, yeah. So an aneurysm can be the cause of a hemorrhagic stroke. That's one cause of a hemorrhagic stroke, like a burst aneurysm. Good question. Okay. This one, I think these three slides, you guys can figure out. I'll give you the answers to this one just so you can kind of have that to go off of. The other one, the other two, I'll let you use as kind of a study guide. But yeah, those are the three or the four or five correct answers here. Okay. But this is kind of what I'm going for with your memorization of the blood clotting thing is like, what's the goal of each phase? Kind of what's the, not like every single step there in the middle, but kind of like what's happening with each phase, primarily. Okay. And then the last two, this, this slide here is just getting at the idea that we have a, we have a bunch of proteins in our blood all the time that are inactivated. And if we just simply activate them, then they kick off the blood clotting cascade, right? And so that's kind of what this is getting at is just going through here and writing in whether this is just a normal plasma protein. Okay, so like the one we were just talking about, plasminogen is a plasma protein that's always in our blood. The liver makes it, it's just always floating around in our blood. But if we turn that into plasmin by TPA, the one we were just talking about, then plasmin's an enzyme now and it goes and it breaks down clots. Okay, so there's like the activated form versus the inactivated form. The inactivated form are just plasma proteins. They're always floating around in our blood. We just need to kind of activate them to, yeah, to kick off that process. Okay, and then the last one is just directly related to that, that other slide, and a couple other things there related to the drugs first, and then a couple other things that are from directly from the notes. So I'll let you guys figure those ones out on your own, but okay. Wanted to at least give you a little bit there because we didn't have time to finish last time. Okay. All right. Yeah, let's see if we can start with that video. Okay, this is just kind of a little intro to the immune system. And let me, of the immune system, and then we'll get into one branch of it, which is called the innate immune system. And then on Monday, we'll get into what's called the adaptive immune system next. Um, so yeah, it's honestly one of the most fascinating parts of the human body, by far. And next to the brain, it's the least understood part of the human body as well. And it's incredibly complex, and we're really just kind of just starting to figure out a little bit of how things work, but it's an incredibly complex part of our bodies. So like this is kind of a broad overview here of what immunity looks like in the body. So when we talk about the innate defenses, of the immune system, what that means is we have the same response to things no matter what it is. Okay, this is just like your body's just reacting against things that aren't supposed to be there, and it'll react the same way no matter what that thing is. Okay, so some of those things are just barriers, right? Our skin, our mucous membranes, these things are keeping things from getting inside. Okay, and then we have internal defenses. Okay, so phagocytes, those would be like the macrophages that were just being talked about in that video. We also have what are called natural killer cells. We talked about those a little bit already. Um, the inflammatory process is part of the innate immune system. We have antimicrobial proteins, similar to the proteins floating around in our blood that are related to blood clotting. We also have proteins floating around in our blood that are antimicrobial. We have proteins on our skin that are antimicrobial too, which just pretty much means when bacteria interact with those proteins, it destroys them. And then the whole process of a fever is also protective, and it is helpful for fighting off infection. And it does it in the kind of the same way, no matter what type of response it is. And then, so our kind of our first line of defense is always just blocking things from getting in the body, right? Second line of defense is to kind of contain the infection and have and slow it down. That's our second line there. And then our third line of defense are specialized weapons that are designed specifically for whatever that exact thing is that comes into the body. And that's called the adaptive immune system, or also known as specific immunity. And so we have our B cells and our T cells that help us do that. So that one on the very bottom there for you in the back, it just said T cells. That's what got uncovered there underneath cellular immunity. So the two branches of our adaptive immune system are the humoral immunity and then cellular immunity. And we'll talk a lot more about those next time, but we'll get into them a little bit today. So, questions on any of this so far? Yeah, Morgan? Not necessarily. It's kind of it could be. Yeah. I guess it could be. Yeah. So something's trying to get into the body. It's got to get through the skin first, right? It's got to break that barrier first. And then once it gets in, the first thing that's going to find it is going to be part of the innate immune system. Not necessarily all of those things underneath internal defenses, but phagocytes are probably going to be the first thing to interact with that thing. Um, and then it'll cause some inflammation. And then in that process, now those phagocytes are also going to help activate the third level of response there. So yeah, it is a timing thing, but it just may not include all of these in the second step. But yeah, great question. Other other questions? Okay. All right, so just a little bit of kind of compare and contrast between these two major branches. So the innate system is completely non-specific, meaning that it's the same kind of response no matter what it is. Um, whereas the adaptive system literally are, oh, I don't know why I did that. Literally our cells design specific things to just match up exactly with whatever that invader or foreign substance is. Okay, so very, very specific. On the innate side, there's no memory. So meaning like the whether we get something in our body one time, two times, three times, is going to be the same level of response. But on the adaptive side, the first time that thing comes in, we don't get much of a response on the adaptive side, but then second time we get a very strong response, and we can most of the time not even be affected by it the second time it comes in, because we have the memory cells as being a part of that. Yeah, so that's kind of multiple exposures. The two main weapons on the adaptive side are called cytotoxic T cells and then B cells that make antibodies for us. Okay, so those are kind of the two parts: the antibodies made by B cells and cytotoxic T cells, cells that are going to go chasing after specific things. And we've kind of already talked about these things here. So, and it's not like they're completely separate. There's definitely some overlap, and you'll see some of that as we go. Okay, so all of this hinges on the idea of an antigen. Okay, we talked about antigens already when we talked about the red blood cells. And so the definition is a substance that can mobilize the adaptive defenses and provoke an immune response. Just like it sounds, it's an antibody generating substance. Right? So anything that inside of our body goes inside of our body and provokes our immune system to create antibodies against it is an antigen. It's an antibody generating substance. And so our own red blood cells are that way, right? Whatever antigen we have, we won't have that antibody. Okay, and so most of our cells in the body have what are called MHC proteins, or major histocompatibility complex proteins. If you think about histo, what does histo make you think of? Huh? Tissues, yeah, tissues, right? The histology is the study of tissues, okay? So all that word is saying is this tissue compatible with the body, right? That's what MHC complexes do, is they're like little ID cards on our cells, right? So our cells have these little things sticking off of them that are proteins, glycoproteins, and that's like the ID card for the cell. And so then the immune system is going to go around and be checking the ID cards of these cells to make sure they're supposed to be there. Okay. And so MHC1 proteins are, yeah, like the passport, like the ID card. These are expressed on all of our cells except for our red blood cells, because they have other types of antigens. And these are just pretty much like the proof that those cells are supposed to be there. Right. And then our immune cells have MHC2 proteins complexes. Okay. And these are like an ID card, but they're a special ID card that lets the body know that these are not just supposed to be there, but these are like the law enforcement of the body. So MHC1 complexes we have on almost all of our cells. MHC2 are immune cell specific. Okay. And there's millions of combinations of different types of MHC complexes in our tissues. And this is where it makes organ donation very challenging. It's not just a simple blood type thing. There's many combinations, many possibilities when it comes to organ donation. And then a lot of people that receive a donated organ still have to take immunosuppressants for the rest of their lives to make sure that their immune system doesn't destroy that organ. So yeah, questions on any of that? Okay. All right, so antibodies. Antibodies are kind of the crux of a lot of this as far as the adaptive immune system goes. They're also known as immunoglobulins, and they're always floating around in our blood. They're part of the plasma proteins. They're always floating around in our blood, like the blood clotting factors, like albumin, like some of these other ones we've been talking about. They're made by our B cells. Okay, the function of them is to bind to an antigen and then either inactivate it so that cell or that chemical can't then interact with anything else, or they can destroy it. Okay, they're usually some kind of a Y shape with two separate antibody binding sites, antigen binding sites. Okay, so yeah, these are always a part of the adaptive system. Okay, so these little shapes here, this is a simple picture and they all look like a simple little Y, but these little shapes are specifically designed to fit a very specific thing. So much so that by the time we're get into adulthood, when our immune system has been fully developed through childhood, um, we have the ability to make around 1 trillion different versions of those antibodies. That means we've been exposed to at least around 1 trillion different types of antigens by the time our immune system is developed. So then we have specific immunity against 1 trillion different types of invaders, right? So one of those things, one of those 1 trillion comes in, that activates a specific type of cell that's hanging out in our lymph nodes, just waiting to be activated. And then it makes a bunch of these antibodies that are going to be specific to that thing only. So that's why it's called specific immunity. Questions on that? Yeah, okay. A and B and all that. Yeah. So there's different, so yeah, there's just different kind of functions of those. And some of them are, yeah, some of them are more likely to be geared towards bacteria. Some are more likely to be geared towards viruses. Other ones are geared towards different types of cells in the body. And then there's even like kind of like different categories as well that aren't necessarily specifically for infections. They're for other things too. And so, yeah, so there's just kind of like these categories to try to help us kind of group them. Yeah. Okay, so let's get into the cells of the immune system a little bit here. So one of the most important cells is the T cells, also known as T lymphocytes. These are part of our adaptive immune system. And then specifically underneath the adaptive, we either have the humoral part of that or the cell-mediated part of that. So T cells are part of the cell-mediated part of that. Okay. T cells are made in the bone marrow, which you'll see in a sec. All of our blood cells are made in the bone marrow, but they mature in different places. And so these mature in the thymus, that gland that was wrapped around our throat. And it's big as a kid and small when we're adults. And so that's why they're called T cells, because they go to the thymus to mature. Okay. Their main job is to recognize an antigen in combination with an MHC protein, and then they help to activate our immune response. So very specifically, our helper T cells are the first ones of this group of cells to be activated, and they will help to activate the rest of the adaptive immune system. So helper T cells are going to be the one that a cell that gets an antigen from like the periphery somewhere, that cell is going to bring it back and show it to a helper T cell. The helper T cell is going to receive it and then activate the rest of the immune system to go after that specific thing. And then we have cytotoxic T cells. These are T cells that are going to be programmed by a helper T cell to go look for that specific thing and destroy it. We have regulatory T cells that kind of help to limit the response. And then finally, memory T cells that are going to be waiting there for a second exposure to be activated. So we've got a bunch of cells ready to go if that same thing comes in again. Okay. And then we got B cells. So B cells are also part of the adaptive system, but they're part of the humoral side. which just means fluid, right? Humor means fluid. Humoral means we're talking about in the blood. Okay, so this is the ones that this is the side of our adaptive system that makes antibodies. Okay, so B cells are made in the bone marrow, just like the T cells were, but they also mature in the bone marrow. They stay there for their maturation process. That's why they're called B cells. Okay, their function is to make antibodies. These are the ones that make the antibodies for us. Okay, and each programmed type of B cell only makes one, right? So how many people have had a cold in the last 2 weeks? Yeah, that's a lot of you guys. Yeah. So you got some virus probably, right? And now you have a host of memory B cells sitting in your lymph nodes programmed for that virus exactly. Right? So if that virus comes back into your body again this week, you'll knock it out. You won't even notice it because your B cells will be ready for that specific virus. It'll release a bunch of antibodies. It'll knock it out. You'll never even notice it, right? So that's what they do. So B cells are the general category. Once we activate one of those B cells and send it into the blood and it starts pumping out antibodies, then we call it a plasma cell. So it's just a different name for the same thing, but it's an activated B cell. That's what it says underneath there. It just says activated form of a B cell. Yeah. Mhm. Yeah. It can be. There's definitely all forms of immunosuppression for sure, but we'll talk about some immune disorders at the end of next class. But one of like HIV affects our helper T cells. So that's one of definitely immunosuppression disease, and that actually destroys the T cell receptors on our helper T cells, and then the helper T cells are required to activate B cells and T cells. And so if our helper T cells aren't working, then we don't really activate any of our adaptive side. So that's one example, but there's definitely many different types of immunosuppression. But that'd be one. Yeah. Yeah, Colby.
You get like a vaccine, is this like the kind of cells that we got?
Exactly. This is what we're trying to do with the vaccine, right? Is we're trying to introduce something that either is like a dead or weakened version of that virus we're trying to protect against, or it's just something that looks like it. So then our B cells will interact with that thing. They'll make a bunch of antibodies against that, pump them into our blood. So now we've got antibodies floating around for that specific thing, whether it's hepatitis vaccine or COVID vaccine, or flu shot, all of those things, right? That's what we're doing. And then we've also now have memory B cells and memory T cells waiting in our lymph nodes in case that thing comes in again. Now we're ready to make a bunch of antibodies and make those cytotoxic T cells. So yeah, that's what the vaccine's all about. Other questions? Great questions. Okay, so take a sec and just kind of a recap here. We talked about this is actually from go back in your notes just a few slides to the one where it's I think it was called blood composition. Those notes we talked about all the different cell types. So yeah, just see if you can kind of fill this in briefly here, and then we'll come back together. So you just writing in the cell type that would have this function and would be a part of this. Okay. So some of this is from these notes, some of it is from that one that was called blood composition.
Now lymphocytes.
Yes, yeah. Mhm. Stands for antigen presenting cell. Can't remember if we've talked about that yet or not, but we will soon. All right, let's go ahead and come back together here. So phagocytic cell, that's typically going to be the first contact. What'd you guys put for that one? Neutrophil, yep, that's right. It's the most abundant white blood cell that we have. We have more of those than any other white blood cell. Ones that are specifically used to kill virally infected and cancerous cells. What'd you guys say there? Natural killer, yep, or NK cells. The ones that are going to turn into macrophages, what were those? Do you remember that one? So when they're in the blood, yeah, somebody was starting to say it, they're monocytes, right? So when they're in the blood, they're floating around through our blood, they're called monocytes. But then they go into the tissue and they're called in because of some problem somewhere in the tissue, some damage, some infection, then they turn into macrophages. Okay. Next one's macrophages. So they destroy invaders, clean up debris, stimulate the adaptive system. Macrophages can act as an antigen presenting cell, an APC, just like in the video. That's exactly what it did in the video, right? That grabbed onto that bacteria, broke it down, saved some little pieces of it, and then went to the lymph node and showed it to a helper T cell, right? That's an antigen presenting cell. Which are the ones that release histamine? Hmm? Mast cells, yeah, for sure. Mast cells. Our other primary APC are called dendritic cells. Those ones are kind of roaming around the tissues and looking for things. The ones that make antibodies, which ones are those? B cells, yeah. The ones that stimulate B cells and T cells, those are our helper T cells. And then we go down to T cells that are directly kind of part of the weaponry of the adaptive system. Those are the cytotoxic T cells. Okay, and then we have memory T cells, and then we have regulatory T cells at the bottom, ones that are kind of suppressing, controlling the immune response so it doesn't get too out of hand. So a bunch of different cells here. These are all leukocytes, right? These are all white blood cells. Questions on any of these? Okay. Everybody got it? Okay. Okay. All right, so we'll start with the innate system. That was just kind of an overview of everything. Now we'll dive into the innate system a bit. So in the innate system, we start with the blocking of things, right? Just keeping things out, right? So we got our skin and our mucous membranes. We talked about this back in BIO1040 with histology. We have this keratinized cells, these cells that are just stocked full of protein, right? That's going to make for a nice barrier. We have oils on our skin, mucus that's in lining cavities like our mouth, our nose, urinary tracts, all those different tracts, right? Those are all just kind of the blocking part of it. Um, on the innate side, we also have chemical defenses. This is some of the stuff we talked about in the skin. Some of it we didn't. But when a virus infects a cell, it goes into our cell, and then it kind of takes over the nucleus of that cell and starts using the nucleus to replicate itself, right? So it activates the the cell's machinery and takes over and makes that cell its slave and makes it replicate itself. So it makes a bunch of virus, right? So that's kind of what a virus does. But then when a cell is infected, it actually is going to release these little chemicals called interferons. Interferons are released all around that cell that got infected by the virus. And that actually warns all the cells in the area to be careful. There's something out there trying to infect us. And so then cells can actually express certain types of proteins on their membranes that will block viruses from getting inside of them. So that's kind of another cool part of our chemical defenses there. And then secondly, we have complement proteins. Complement proteins are similar to blood clotting proteins, how they're just floating around in our blood all the time and they're not activated. But then if the right thing interacts with one of those complement proteins, it activates it. And what it does is it then creates those proteins become activated. They form these little complement protein pores, and they start poking holes in cells in that area, so much so that cell bursts and gets destroyed. Okay, so that's one of the effects, is causing cell lysis, but then also activating our complement proteins will also cause just activation of the whole immune system. So these are all just things that are in our blood helping us, or in our cells helping us fight against invaders. The bottom two bullet points, the first one says form pores in the infected cell to cause lysis, which means like the cell bursting. And then the second one says stimulate immune cells. Okay, so that's kind of our overall defense of the innate system before we get into the actual cells. When we get into the actual cells, it's a lot of these that we've already talked about, right? So the neutrophils, natural killer cells, mast cells, macrophages, kind of tells you what types of cells they each go after and some of the ways that they do that. Okay, so they can induce apoptosis, like in that video I showed you on the natural killer cells before, which pretty much means it forces the cell to destroy itself, right? Programmed cell death is apoptosis. And so if you cause enough damage to the mitochondria, to the DNA of a cell, then the cell will destroy itself. And natural killer cells will cause cancerous cells to do that. Yeah, and so just a bunch of different cells and how they work there. Another part of the innate system is the inflammatory process. Okay, so we've all dealt with inflammation anytime we get a virus or even just a bruise or our legs, our knees hurting after exercise, something like that, is some form of inflammation, right? And there's 4 classic signs of inflammation. Those are heat, redness, pain, and swelling. When something's inflamed, it gets warm, right? Turns a little bit red, it hurts, and then we notice some extra fluid in that area too. Okay. In more sports medicine, kinesiology, you might see a 5th sign noted, which is impairment of function. Okay, so maybe that's like some stiffness or some lack of range of motion, something like that, lack of strength, something like that is typically part of the inflammatory process too. So we're going to kind of walk through how we activate the inflammatory process with some details here, and then we'll kind of put all that together here, and we'll kind of connect it to what causes the heat, what causes the redness, what causes the pain, what causes the swelling. Okay, so whenever we have an injury in our body, we damage some cells, right? Some cells are damaged, they're broken open, okay? And when that happens, all the stuff that's supposed to be inside of cells gets dumped out, and it goes floating around in that interstitial space. We've talked about that already in terms of swelling, that causes swelling. But some chemicals inside of our cells, when they're released out into the interstitial space, they activate the immune system. Okay, so damaged cells are going to release cell contents. Okay, and so that's going to activate the immune system. And part of those contents is histamine. We have histamine inside of our cells. But then also any damaged cells can also activate mast cells that are in the area. And those mast cells release more histamine. Oops, sorry, keeps doing that. And so when we release histamine, histamine is a vasodilator, which means it opens up blood vessels. So that's going to lead to the heat and the redness part of inflammation, right? We're sending more blood to an area. So that is going to cause that area to become red and to get warmer because of that blood we sent there. Okay. Other chemicals, we have one in particular called substance P that is inside of our cells. When we release it, it goes out and binds to pain receptors, to nociceptors, and that's going to cause pain. Okay. And then vasodilation is going to lead to vasodilation that was caused by histamine is going to lead to delivery of a bunch more things to that area because we're sending more blood there. Okay. Some of those things are white blood cells, right? So we get more neutrophils, more monocytes there. And then also clotting substances, which is helpful too, right? So we're sending more clotting proteins. If we have a broken blood vessel, that helps to slow down the bleeding. Okay. But that vasodilation is also going to be part of leading again to that heat and that redness. Okay. Then the vasodilation is also helpful for getting rid of some of these things that are released from broken cells and broken tissues. We need to get that stuff out of there. Okay. But then some of these chemicals too, some of these cell contents and histamines, they also change the permeability of our capillaries. Okay. So our capillaries are the little tiny blood vessels where we allow for exchange of oxygen and CO2. There's normally cells that are really close to each other there. When we activate the immune response, those cells actually move away from each other a little bit and open up the gaps between there. So then things can get through and get into that tissue space. So that could be more white blood cells, that could be proteins, all those things that are going to help us go in there and deal with the problem that's in the tissue. Okay. And so, yeah, so all of this is going to lead to the swelling part of the inflammatory response. So that last blank that uncovered there on the very bottom just says swelling. Okay, so by sending more blood, the vasodilation part, and by opening up our capillary beds and letting more things through, that's going to be connected to the swelling that we get during inflammation. Okay, questions so far? Okay, it all starts with broken cells, right? Damaged cells are going to activate this whole thing, and then it kind of leads to all of those symptoms that we just saw. Okay, a few more steps here. Since we're delivering more blood to the area with vasodilation and the capillary beds are getting more permeable, that means we can get more phagocytes to that area in a process called chemotaxis. Okay, chemotaxis is when cells aggregate to one specific area. Okay, so all the immune cells are being drawn to this area where the damage is because of the histamine, because of the other chemicals released by those broken cells. So that's causing chemotaxis. So we get more neutrophils, more macrophages in that area. And then definitely the blood clotting process happens. So we stop the bleeding that occurs there. And then all of us have had probably zits with some white stuff in them or other types of skin injuries that end up getting this white liquidy stuff inside of it, right? Pus, pretty gross. Nobody really wants to talk about pus, but really what that is just the dead version of all this stuff, right? So the neutrophils got there, they did their job, they phagocytosed a bunch of stuff, but then they eventually die and they're just kind of there. Same thing with some of the macrophages, bacteria that was there, other debris from the injury site. It's just all turns into this whitish substance called pus. Okay, go ahead. Yeah, no, it's not necessarily bad. The only risk is risk of infection, right? And so as long as you're keeping it clean, then it should be fine. But that's really what a zit is an infection anyways, right? And so it can be helpful to get that stuff out, as long as then you're keeping it clean. And you know, a lot of the acne creams will have certain types of acids in them and stuff that you can put on that then will knock out all the bacteria in that area. So then the infection doesn't reoccur. But yeah, it's usually a good idea to kind of clear it out. But you know, some dermatologists might say like, don't get too crazy about popping them because then you've got all these like open sores on your face with, you know, then you're losing your first line of immunity by having a hole there where things can get in. So yeah, Summer. Mhm. Yeah. Yeah, so it's all internal, and that's going to be just all the stuff that leaked into the interstitial space because you have broken blood vessels underneath the skin. So it's dried up, not dried up, but it's just like kind of blood that just got stuck out there, proteins, other things like that. And so now it's the job of your immune system. Your macrophages will come in there and eat that stuff up and remove it, and your neutrophils, and then your lymphatic system will try to be removing that stuff as well. So yeah, you can't really help it as much. You could with a little bit of massage, actually. A lot of times when you have a deep bruise in your muscle, you'll feel like some like hard kind of like chunks in there. Some massage can kind of help break that up, and that just kind of helps speed up the process so it moves through your lymphatic system a little bit quicker. But yeah, yeah. Other questions? Okay. All right. Go ahead and talk about this question with the people on your team and send in your answers when you're ready. I think so. Yeah. I skipped a couple. I just answered it for you. Then I realized why I had added those later because I only had one beyond that. So yeah.
Yeah. You have a backup? Like for.
All right, go ahead and put in all that are true and hit the send button, please. Make sure to hit send. I'll leave it open for a sec, but it looks like still need a few more. Just make sure to hit that send button on your clicker. This is the only clicker question today. So if this one doesn't go in, then you won't get any points for the day. It's like quite a few people weren't concerned about that by the fact that there's only 34 responses out of 48. I know Camp Love is tonight, so a lot of them were gone for that. But okay, all right, we got 34. That's probably what we got. All right, so which of the following lead to pain? Okay, most of you said A and B. That was pretty much what all of you said. So A, cell contents binding directly to nociceptors. That is true. And then we get that pressure caused by swelling. That could definitely be true. But then this one, probably not so much, right? This one is probably really, if anything, maybe slowing down the pain because we're not leaking as much fluid into that interstitial space. But vasodilation would be what leads to this swelling, right? Delivering a bunch of stuff to that area, leads to that pressure, leads to the pain. Chemotaxis is a part of that too. So all the extra stuff in the interstitial space, including the cells that migrated to that area via chemotaxis, that's going to be a part of the swelling as well, which leads to some of the pain. And the cells that go to that area release chemicals that also cause pain too. That's part of what leads to pain with inflammation. Is macrophages go to that area, they are eating stuff up, and then they release other chemicals that activate pain receptors too. So everything except the blood clotting. Okay. All right. Yeah, I guess you got one more clicker question here. But yeah, so this is just kind of a flow chart to walk you through that. Okay. So it really starts with this whole thing of we're releasing histamine and cell contents, right? And then from there, we have our three main responses, right? So our first main response is vasodilation. That was directly caused by the histamine, right? And then the other main response would be increased capillary permeability. Our capillaries get leakier, right? And then our third one, well, yeah, then we got pain directly from the cell contents, okay? But then our third one would be chemotaxis, right? So we're sending a bunch of leukocytes to that area, okay? And then the red boxes there are those signs of inflammation, right? So pain can be directly caused by the cell contents, okay? The vasodilation is going to lead to increased blood flow. That increased blood flow we know is connected to both the heat and the redness part of inflammation. Okay, the increased blood flow also helps us deliver more cells to that area to help with the process and deliver clotting factors to slow down the bleeding. So we got blood clotting, and then, yeah, that's it there. And then increased blood flow helps us to clear stuff out of the area too, right? Clearing out toxins and debris. That increased capillary permeability allows fluid and white blood cells to enter the interstitial space, which is helpful for clearing out stuff, but it also leads to swelling because it's some of the stuff that's stuck out there, right? And then that chemotaxis is helpful because we got to get those white blood cells there to help clean up and fight the infection, but that also leads to swelling as well. So it's kind of this balance, right? Of like, we don't want to knock out our inflammatory process completely when we have an injury, right? But it can tend to go a little bit stronger and a little bit more intensely than we want it to, and that can slow down the healing process. I mean, the whole point of taking Advil, getting a cortisone injection, all those things is about decreasing inflammation, right? But obviously, all of these things are important because they help us heal. So it's like this balance of how much do we dampen that to speed up the healing process, and how much do we let it happen to actually let ourselves heal. Okay, another one of those things that doesn't feel helpful, but is a fever. Okay, so a fever is when we have some form of systemic inflammation, and it makes our body temperature rise. Okay, normally our body temperature is somewhere around 98.6. During COVID, it was the biggest time of data collection for people taking their temperature for centuries, right? Because everybody was taking their temperature all the time. You had to walk into restaurants, take your temperature, do everything. And so they actually discovered during that time that 98.6 isn't actually the average body temperature of people anymore. It's actually maybe a degree or so lower than that. And that was just kind of, the 98.6 was yeah, decided like 150 years ago or something. And so it was just an interesting thing that came out of that. But the bottom line is our bodies are set at some set point temperature, just like a thermostat, right? And if we get below that, we do things to warm ourselves back up. If we get above that, we do things to cool ourselves down, right? The way we warm ourselves up is by increasing our metabolism in our cells or by shivering. The way we cool ourselves down is decreased metabolism or sweating, right? And so when we get a fever or when we get an infection, that those microbes, the bacteria and the cell and our cells themselves can release chemicals called pyrogens. And the pyrogens actually go to our brain, to our hypothalamus, where our brain's thermostat is, or our body's thermostat is, and pretty much just goes in there and cranks up the temperature a little bit, right? That's pretty much what pyrogens do, is turns up our thermostat. So the first part of having a fever is you feel cold, right? Because the thermostat just went up. So your body temperature is below what it's supposed to be according to the thermostat, right? So you get shivery, you get cold. And then you warm up, your body increases temperature to that new set point. And then you kind of feel fine. You don't feel great because you're hot. And when your body's too warm, it can actually help to kill bacteria. It can make it actually reduces the iron level in our blood, having a high temperature, which makes it so bacteria can't thrive as well. So those are the things that are helpful with fever. And the reason we get the chills is because we're colder than our set temp, right? But then we take some Advil or some Tylenol that goes in and blocks the pyrogens, turns our thermostat back down. Now we get super hot, right? Now we start sweating. You guys have had it before, probably, where you just like completely soak your bed with sweat, right? When you're sick, because now you're taking that set, you're going back down below that set point, right? You're moving your body temperature back down because your set point went back down, right? So should we try to reduce fevers? Fevers are actually helpful for fighting sickness. But they're dang uncomfortable, right? They're very uncomfortable. They make you feel terrible, right? And that's so it's kind of up to you. The last time my wife and I got really sick last semester. I was telling her I was trying to be tough and like tough it out the first couple days, like, and we had like 103 fever, both of us, and like she was like, just take medicine. I'm like, no, I'm gonna try to help it fight this off, and then I gave up about 48 hours later. It was like so uncomfortable. So yeah, but it can be helpful. In kids have a harder time regulating their temperature than adults do. And so you can, in kids, it can turn into a seizure, febrile seizure, if the brain gets too hot. And yeah, and so it can definitely be dangerous in that point. But yeah, so typically in kids, you treat them, especially if they're high. Mild fevers, you definitely don't need to, but moving up towards 104, 105, you definitely want to treat those fevers for sure. So, all right, guys, that's it. Have a great weekend. We'll see you on Monday. Bye, Isabel.